Welcome to the Agrawal classes. I am Ajit Agrawal and we are studying thermodynamics for engineering students. Today in the 16th class and tutorial 4, we will study the entropy change with the help of some numericals. As we had discussed in the previous class, the processes in which the entropy change we had calculated and we had obtained the derivations for all the processes. So in this particular class, we will utilize that particular equations to find out the change in entropy in the process. Let us consider the first question. An iron cube at a temperature of 400 degrees centigrade is dropped into an isolated bath containing 10 kg of water at 25 degrees centigrade. The water is finally reached a temperature of 50 degrees centigrade at a steady state. Specific heat of water is 4186 joules per kg Kelvin. Find the entropy change for the iron and water. Is the process reversible? If so, why? So in this particular question, we have to find out the change in entropy, and then by finding out the change in entropy, if it is 0, then we'll say the process is reversible, and if the entropy change is more than 0, then we'll say the process is irreversible. So first we'll assume to find out the change in entropy as 273 Kelvin temperature as a base temperature, because all the temperatures given are above that, so we'll consider 273 as a base temperature. So let us find out the heat loss given by the iron cube is equal to the heat loss gained by the water. We know this because this is a insulated one, so heat gained by the water is equal to the heat loss by the iron cube. So let us, Mi is the mass of the iron, Cpi is the specific heat of the iron, and this is the change in temperature. So that is the heat loss by the iron, and Mw is the mass of water, Cpw is the specific heat of the water, and this is the temperature change, that is 323 final temperature and 298. So whatever the heat is given, this heat is taken by this. Substituting the value of mass 10 kg given, specific heat of water 4186 joules per kg Kelvin is given. So we come to know MiCpi is equals to 2990. Now we'll find out the change in entropy. To find out the change in entropy, we will find out the entropy of the iron at the initial temperature, that is 673, and the entropy of the iron at final temperature, that is 323 Kelvin. So entropy of the iron at 673 Kelvin is MiCpi log of T2 upon T1, that is 673 upon 273. So it comes out to be 2697.8 joules per Kelvin, because mass is there. So it is joules per Kelvin. The entropy of the iron at 323 Kelvin is, again we are using the same formula, MiCpi log of T2 upon T1, 323 upon 273, because we are taking 273 as a reference point. So the entropy of iron is 502.8 joules per kg per Kelvin at 323 Kelvin. Similarly, we'll find out the entropy of water at 298 Mw Cpw log of 298 upon 273 comes out to be 3667.8, and entropy of water at 323 Kelvin is equals to Mw Cpw log of 323 upon 273. So we calculated the entropy of this. Now we will sum up the entropy of iron. We'll find out the change in entropy of the iron cube from the initial to final, what is the change, and similarly for the water also we'll find out the change in entropy. So I'm writing here again, change in entropy of iron is 502 0.8 minus 2697.8 joules per Kelvin, that is equals to 2195 joules per Kelvin. Similarly, change in entropy for the water is, final entropy is 7040.04 minus initial entropy 3667.8 is equals to 3372.24 joules per Kelvin. So, in this particular process, the change in entropy is minus 2195, and in this case, the change in entropy is this one. So, the net change in this process is net change in entropy is equals to minus 2195 plus 3372.24 is equals to 117.24 joules per Kelvin. So, first question, find the change in entropy. So, find the change in entropy of the iron is minus 2194. Change in entropy of water is 3372.24. And is the process reversible? So, in this case, the change in entropy is plus. Net change in entropy is plus. So, the process is irreversible. If it comes out to be 0, then we'll say the process is reversible. And if it comes out to be negative, then we'll say this particular process is impossible. Let us consider the second question for the entropy change. An ideal gas is heated from temperature T1 to T2 by keeping the volume constant. The gas is expanded back to its initial temperature. According to the law, PV equals to constant. PV to the power n equals to constant. If the entropy change in the two processes are equal, find the value of n in terms of the adiabatic index gamma. So in this particular case, we are given the two processes. One is the constant volume process and second is the polytropic process. And for both the process, the temperature range is same. So we will find out the entropy change during a constant volume process, and then we will find out the change in entropy during the polytropic process. So here the change in entropy during constant volume process is this mCv log of T2 upon T1, and the change in entropy during polytropic process is mCv gamma minus n upon n minus 1 log of T2 upon T1. So we'll equate these two entropy change. So it will come gamma minus 1 upon n minus 1 equals to 1, or n equals to gamma plus 1 by 2. That means the value of n in terms of adiabatic index will be gamma plus 1 by 2. So this is very simple question. Let us consider another question. 1 kg of gas is enclosed in an isolated box of volume V1, temperature T1 and pressure P1. Is allowed to expand freely till volume increases to V2 as V2 is equals to 2V1. Determine the change in entropy and take the value of R for gases 287 joules per kg Kelvin. In this particular process, during the free expansion in an isolated box, delta U, or the change in internal energy, will be 0. The work done will be 0, as we know, and from the first law of thermodynamics, Q is equals to delta U plus W. So delta U is 0 and W is 0. So the heat supplied is also 0. This process we can represent on the PV diagram like this. Here the volume V1 and pressure P1, and the volume is doubled, so say up to this point. So this is the process from 1 to 2, where the volume is V2 and here the volume is V1. So in this particular process, as this is an irreversible process, we are representing it on the PV diagram by a dotted line. Now to calculate the change in entropy, we'll assume this free expansion process is replaced by an isothermal process, reversible isothermal process. So that process we can represent on the TS diagram as this process 1 to 2 isothermal process, that the temperature is constant, and will apply because the change in internal energy in this case is also 0. And now we will try to find out the work done, and that work done will be eventually equals to the heat supplied. So we will find out the change in entropy. So applying the first law of thermodynamics to this isothermal process, delta U is 0. So Q minus W equals to delta U from the first law of thermodynamics. So Q is equals to W. And we know that the W is given as PdV for a closed system, where this can be expanded from 1 to 2, and we can get as the work done P1 V1 log of V2 by V1. This we had done earlier also. So this is the heat supply. This we can write as MRT, or for 1 kg we can write RT. PV is we can write as RT log of V2 upon V1. So this we can write as Q by T is equals to R log of V2 by V1. And this is nothing but a change in entropy during the process 1 to 2 if I am considering isothermal process. So this is the change in entropy, and substituting the value of R, 287 log of 2, because V2 is 2V1, so it is log of 2. So it comes out to be 198.9 joules per kg Kelvin. So that is the entropy change during the irreversible process. Let us take another question to find out the change in entropy. Calculate the change of entropy of 1 kg of air expanding polytropically in cylinder behind a piston from 7 bar and 600 degree centigrade to 1.05 bar. The index of expansion is 1.25. So in this case, this is a polytropic process, so we will use the change in entropy, a general formula which we had derived as S2 minus S1 Cp log of T2 upon T1 minus R log of P2 upon P1. So in this particular equation, we know all the values except the temperature T2. So to find out the temperature T2, we'll use the relation T2 by T1 is equals to P2 by P1 to the power n minus 1 upon n. In this case, we'll substitute the values. So T2 will be equals to 873. Here remember 600 degrees centigrade is given, so we are adding a 273 to make it Kelvin into P2. P2 is given as 1.05 divided by P1 is given as 7 bar to the power 1.25 minus 1 divided by 1.25. So when you solve this, the temperature comes out to be 597.3 Kelvin. So now to find out the change in entropy, we'll directly substitute the values here. Cp for the air, we know that 1005. Instead of writing 1.005, I am writing 1005 joules per kg Kelvin into log of T2. T2 is given as 597.3 here, divided by T1. T1 is given as 873 minus R. R for the air we know as 287 multiplied by log of P2. P2 is given as 1.05 and P1 is given as 7. Here also I can write 10 to the power 5, 10 to the power 5 in terms of Pascal. So when you substitute the values, you will get the change in entropy is equals to 0.1626 kilojoules per kg. Then there is another way you can find out if instead of using this formula for the polytropic process, we have another formula as S2 minus S1 is equals to Cv into n minus gamma upon n minus 1 into log of T2 upon T1. So here this is the specific heat during the polytropic process. So we'll substitute the values here and we'll get this answer 0.1626 kilojoules per kg. So basically in the polytropic process, either you can use the general equation or you can use this equation to find out the change in entropy. So only unknown was the temperature. So you have to just find out the temperature and substitute the values. In the last question, in an air turbine, the air expands from 7 bar and 460 degrees centigrade to 1.012 bar and 160 degrees centigrade. The heat loss from the turbine can be assumed to be negligible. Show that the process is irreversible, and second is the calculate the change of entropy per kg of air. So first we will draw the TS diagram. On the TS, this is the constant pressure line. Here I am selecting point 1 as 7 bar and temperature 460, that is 733 Kelvin. And if it is adiabatically and reversibly expanded, then it is a vertical line constant entropy process. So this is the point 2. But in this particular case, say the process is coming up to 2 dash and here the temperature is given as 433 Kelvin, that is 160 degrees centigrade. So first we will assume this as a reversible adiabatic process or simply an adiabatic process, because the heat loss from the turbine is given as a negligible. So we can assume it as 0. So for 1 and 2 we have the relation T2 by T1 equals to P2 by P1 to the power gamma minus 1. Here gamma we are taking because we are assuming this process as an adiabatic process. So T2 is equals to 421.6 Kelvin, that is 148.6 degrees Celsius. So this point is 421.6 Kelvin, it is lower than this. And then as this process is adiabatic, then how come this temperature is increased? So what actually happens in the turbine when the air expands? Although there is no heat loss going out, no heat transfer, but what happens, because of the fluid, the air which is passing through this turbine, it has the viscosity, and because of that the heat is generated there, and that heat is taken away by this air only or this fluid only. So because of that, the fluid temperature instead of 421.6, the heat is generated and that heat is taken away by that fluid. The temperature is increased to 433 Kelvin. So that way, whatever the heat is generated, that is carried away by the fluid only. So there is no heat transfer as such. So that is that temperature rise. Now we have to find out the change in entropy per kg of air. So actual process is now 1 to 2 dash, because the temperature is not 421.6, the temperature is 433. So this 2 dash point will move towards the right side, because if this process is possible, then the entropy has to increase. So that way the 2 dash point will always be on the right side. It will not be like this. In this case, the temperature will reduce and the entropy will also reduce. So this is not possible. So to find out the change in entropy from 1 to 2 dash, we can write S2 dash minus S1 final point minus initial point. S2 dash minus S2. S1 we can write instead of S2, because 1 to 2 we had considered as a constant entropy process, reversible adiabatic process. So S1 can be replaced as S2. So now we are finding out the change in entropy during this process, because in this process there is no change in entropy. Only in this process there is a change in entropy. So if we'll find out this change in entropy, then it will be the total change in entropy from this point to this point, or this state to this state. So for this is a constant pressure process. 2 to 2 dash is a constant pressure process. So we can write down the formula Cp log of T2 dash upon T2. Substituting the values, you will get this 26.81 joules per kg Kelvin is the change in entropy, or 0.02681 kilojoules per kg Kelvin. So this is the change in entropy. So we can say this process is not a reversible process. This process is actually an irreversible process, because the entropy has increased. If this comes out to be 0, then we will say this process is reversible. So in this case, it is an irreversible process, and this is the change in entropy. So that way we had covered in this class the 5 number of numericals related with the entropy change, and we had used the formulas which we had developed in the previous class. Thank you.